Hello, ladies and gentlemen. As I'm talking to you right now, my computer is sitting on the front desk by the smartboard, and I am standing by the phone. You may have a hard time hearing me if you can hear me at all. You may have decided to adjust the volume level on your computer in order to be able to hear what I'm saying. The fact that I'm standing far away obviously makes it harder to hear. I'm approximately 14 meters from the computer. Now I'm standing 10 meters from the computer. Very likely you are able to hear me a little bit better, but I'm still fairly faint and you may have to strain in order to hear what I'm saying. I moved 4 meters closer. I'm going to move another 4 meters closer. Now I am approximately 5 meters from the computer. Most likely you can hear me quite a bit better. I will approach. Now I am standing only 1 meter from the computer, and you should be able to hear me as you normally would have in all the other lessons that you've done. This is not a really big surprise that when somebody approaches you, if they're speaking at the same level, that you are able to hear them a little bit better, and in fact sometimes quite a bit better when they're a lot closer to you. That's the topic of our conversation today, is about what we call sound intensity. And right on cue, there's somebody appears to be waxing the halls right outside the classroom. Hopefully they won't interrupt us too much. So the idea of sound intensity. When any kind of sound is emitted, whether it be somebody talking or a tone or from the GLX that I showed you today, or the note from a musical instrument, it's emitting energy. That energy is vibrations, found in vibrations. It's kind of kinetic energy, sound energy, if you will, and that energy spreads out in all directions. We could say 360 degrees, but that's even making it too simple, because that implies that it's a two-dimensional circle. It's actually heading out in a three-dimensional spherical pattern in all directions. As it gets further from the source, the energy becomes more spread out. This is why sound is not as loud. So we come up with this term, sound intensity. So it's a measure of the sound energy, as we discussed just a second ago. But it's a little bit more than just looking at the sound energy. It's the sound energy per second per square meter. At a given distance from the source. Or you can think of it as being from a particular point in space. If we take a look at this diagram here, you see what we could talk about, what we're talking about. The sound is being emitted from this green spot right in the middle. The total amount of energy stays the same as it radiates away. If it's just one simple pulse or something like a hand clap, the total energy from that hand clap has to remain the same, conservation of energy. But what happens with the sound wave is it spreads out over a larger area the further away you get. If we're a distance of r away from here to this point right over there, we could say that a little bit of sound is going to take up this certain area. So let's say the sound is directed in just that general direction. We could extend this to be all around it in 360 degree circle, or 4 pi in terms of the entire sphere. You guys haven't learned that math yet, but you probably will soon when we're talking about three-dimensional surface, the three-dimensional objects. But let's say we can limit the energy as being projected in this one direction. So all of the energy is going to be spread out over this area, and we'll call that area A. When we go twice as far out to here, we've gone 2R. Well, every dimension is going to be increased. So you're going to, if you double the radius, you double the height of that little rectangle, and you double the width of that little rectangle as well, which gives you, as you can see here, 1, 2, 3, 4 little bits of area. So you get 4 times the amount of area. If you have 4 times the amount of area, but the exact same amount of energy being at this point here as you did at that point here. You have the same amount of energy, but you have it divided up into a smaller amount of area. That means that the sound energy per unit area goes down by a factor of 4, which is 2 squared. So when you double the radius, you get a quarter of the energy. If you had 10 times more radius, if you were going 10 times further from the source, you would have 100 times less sound intensity. Right? Very similar to the gravitational force formula that we saw in an earlier unit. So when we look at the idea of sound intensity, and we look at what the sound intensity actually is, it's an energy per second. So energy is in joules per second, and all of that is per square meter. Now, if you look at the idea of a joule per second, you should have an idea of what that represents, because we looked at it a couple of chapters ago. A joule per second, energy per unit time, that is power, and so that's equal to a watt. So the sound intensity unit is watts per meter squared. When we talk about sound intensity, it's a little bit different from the idea of loudness, and we're going to see this theme popping up a couple of times in the next chapter and a half, chapter 6 and 7 in your textbook. The difference comes about because sound intensity is an objective term. It is something that can be measured with an instrument. It doesn't matter who's observing it. The sound intensity should stay the same. Loudness is subjective. Subjective means it depends on the subject that is making the observation. So I may find a particular sound really, really quiet because it might be in an extreme range that where I don't hear very well. You may find that same sound very loud. So what is loud and what has a large volume and a small volume is a subjective idea, because it really does depend on your hearing. So a sound can be very, very intense, but impossible to hear for anybody. So you can have a lot of energy being transferred. Think of an ultrasonic wave that may be able to shatter glass, for example. That is a lot of energy, but we don't hear it, so it's not very loud. That being said, if you can hear the sound, there is a very close tie between the sound intensity and the volume. The higher the sound intensity is, the more volume you're going to have. So the problem that we have with sound intensities is that the values that we get in watts per meter squared can vary quite a bit. If you look in your textbook, there is a chart. I can't remember exactly where it is at this moment, but you have a chart in your textbook showing you different sound intensities for different events. Okay, remember that sound intensity is an objective term, so it doesn't really matter who's making the observation. That chart is found on page 248. So by definition, we have a different system that we're going to be using. But when we're looking at watts per meter squared as the way of measuring sound intensity, a person whispering from 2 meters away. You've all been in a conversation, we've been whispering, maybe not 2 meters away, but if you're going to whisper to somebody 2 meters away, it has a sound intensity of 10 to the negative 10 watts per meter squared. That means that the power of the sound reaching you, if you're 2 meters away, is 10 to the negative 10 watts for every meter squared. So when you think of the sound hitting your eardrum is about maybe a 10,000th of a meter squared. Let's say a 1 centimeter by 1 centimeter, which is a 10,000th of a meter squared. So if you get 10 to the negative 10 watts hitting a full square meter, you'd only get a 10,000th of this, or 10 to the negative 14 watts hitting your eardrum. So that's not a lot of energy. So every second, 10 to the negative 14 joules of energy is hitting your eardrum. It's a very, very small amount. If you were to look at a slightly louder sound, say like a conversation between two people, maybe this kind of level, we're looking now at around a sound that is about 1,000 times more intense, which makes it 10 to the 3 times more intense, which makes it 10 to the negative 7 watts per meter squared, which is still a really, really low number. A very loud conversation might be 10 times more than that. Imagine 10 people trying to talk to you at once. That would be 10 times louder than that, or somewhere in the neighborhood of 10 to the negative 6 watts per meter squared. Still, when you consider that that's watts per meter squared, and your eardrum is only about 1 centimeter squared, which is 1/10,000 of that, you're only looking at about 10 to the negative 10 joules of energy hitting your ear each second. Still a really small amount. And that's why when we talked about energy transformations earlier on in the course, we said that sound does take some energy, but it's not a lot, so it doesn't really factor in quantitatively with how much energy that we have in a particular energy transformation. Even something that is considered very loud, like a rock concert. So if you're at a concert and you're up close to the speakers, up close to the stage, it can sometimes reach up to about 1 watt per meter squared, which is about 10 billion times more intense than the whisper. Normal human perception, for you to be able to tell that there's a noise, if you've got good hearing, is around 10 to the negative 12 watts per meter squared. So we're very in tune with what we have, with the sound capabilities that we have, because it's not a lot of energy. Here's the issue that we have. Look at these numbers. We have a number here like 1 watt per meter squared for something that's really, really loud. We have 10 to the minus 6 for a really loud conversation. That's 1,000,000 times less. 10 to the minus 7 for another conversation. We have 10 to the minus 10 for a whisper. Those are huge differences in numbers. So let's say that I wanted to make a quick little bar graph here. So sound intensity, we'll just call that SA, or SI I should say. Sound intensity in watts per meter squared. Let's say we're looking at levels of conversation. So I'd say, okay, well here's 10 to the negative 6. This is a loud conversation. I want then to put on this graph what a quiet conversation would be like. It's about 1/10 of that. So maybe this. That's a quiet conversation. We can see the differences between these two things. They're obviously different. This loud one is obviously 10 times larger than the quiet conversation, so it's 10 times more intense. Here's the issue. Let's include the rock concert on this chart. So if I want to include the rock concert, and we're still going to have our sound intensity here in watts per meter squared, it has to go all the way up to an intensity of 1. So here is my rock concert. Well, now let's look at my loud conversation. It's 1,000,000 times less intense than that. So how do I draw that? Okay, I'm going to give it an attempt over here. That's probably still a little bit too high, but that's my loud conversation. So if that's my loud conversation, what does my quiet conversation look like? 10 times less than that? And how would I be able to tell, really, maybe a little bit lower, maybe not, who knows, it's kind of tough to draw here. how can I really tell by looking at that they are different at all? It's sometimes meaningless to look at the difference. Yes, those two values on the right are 10 times less than each other, but they're insignificant compared to the rock concert. And so we would be able to easily tell the difference between this quiet conversation and loud conversation, but you can't numerically really tell the difference between the two. They're essentially the same thing. It's difficult to compare numbers that are so far spread out. So we don't use this sound intensity in watts per meter squared in normal circumstances to measure how intense a sound is. We use a different system. The system that we would normally use for graphing and for explaining this concept would be a linear scale. Linear scales, you go up by the same amount. If you double one value, you end up doubling the other value. So if you, for example, had a conversation that was twice as loud, your sound intensity would be twice as much. That is a linear scale. But it doesn't work here because of the huge differences in number. So what we do is use another version of a scale. It's called a logarithmic scale. I think you've probably started looking at logs in math class. I believe that's something that's done in grade 11. We're going to go over the very, very basics here of logarithms. So the whole idea here is that a change in one bell, this is the unit that we use for sound intensity in a logarithmic scale, or you can use a capital letter B, represents a change of intensity of 10 times. You probably haven't heard of it as bells, but instead as decibels. So one bell is 10 decibels, or decibels. So we call this the decibel system. And 10 decibels, increasing 10 decibels in the decibel system means a 10 times increase in sound intensity, which sounds kind of linear, but as you're going to see, it's not. So if we had an increase in 50 decibels, which is 5 bells, that represents an increase in sound intensity. Your first reaction would be, say, well, it's 50 times more intense. But that's thinking in a linear way and not thinking in a logarithmic way. So 50 decibels really means if you're going to go from 0 to 10, that is 10 times more intense. From 10 to 20, that is another 10 times more intense. From 20 to 30 is another 10 times more intense. 30 to 40 and 40 to 50 are each 10 times more intense. So the total is 10 times 10 times 10 times 10 times 10, or 10 to the 5 times more intense, or in other words, 100,000 times more intense. Well, that's a lot different than 50 times more intense. 100,000 times more intense. So the basic idea here is that we go 10 to the x is the change in sound intensity. So change in sound intensity, and notice we don't have a symbol for this, so I'm just kind of making them up as we go along here. The change in sound intensity is 10 to the x, where x is the difference in bells. In order to get the difference in bells, when you have decibels, you divide by 10. So let's look at a couple of examples to see how this works on the next page. A sound has an intensity of 60 decibels. What is its intensity in decibels if it is 1,000 times less intense? So if you take this 60 decibel sound and you make it 1,000 times less intense, what is the new decibel level going to be? So you may be able to just look at this because the numbers here are really easy. You might be able to look at this and say, well, 1,000 times less intense. That's 10 to the 3 times less intense, which means because of this 3, it's 3. You have to go down by 3 bells. If it's less intense, you go down by 3 bells, or 30 decibels. So you start from 60 decibels, you go down 30 decibels, and you end up with a sound of intensity 30 decibels. So you might say, oh, it's half as intense, but no, it's not half as intense. It's 1,000 times less intense. It has an intensity of 1,000th of a 60 decibel sound. So if you're thinking it's half of intense, you're thinking in a linear scale, and you need to get your mind out of the linear scale into a logarithmic scale. How many times more intense is a 75 decibel sound than a 15 decibel sound? Well, the change in the decibel level is 60 decibels, which means 6 bells, which means that the sound intensity change is 10 to the 6, or 1 million times more intense. So the sound intensity is 1 million times more intense. It's not 5 times more intense, because 15 times 5 is 75. It's 1 million times more intense. On the next slide, we're going to look at a couple of examples where the numbers don't work out evenly, and we're going to look at some of the math that goes behind this. So let's say, in this case, your change in decibel level is 88 minus 43, which is 45 decibels, or 4.5 bells. Do the exact same thing as we did last time. The change in sound intensity is equal to 10 to the 4.5. So again, you have to be very, very careful about this. This is not, we know what 10 to the 4 is. 10 to the 4 is 10,000. 10 to the 5 is 100,000. So you may look at this and say, well, somewhere between 10,000 and 100,000, so let's call it 50,000. But again, you're partially thinking in a linear sense if you're doing that. So a couple of different ways of doing this. The easiest way by far is to pick up your calculator and type in the number 10, and somewhere along there you should have an X to the Y button. Press that and type in 4.5 and equals, and it should give you 31,623, we'll say. There's more decimal places after that, but that's good enough for our purposes. So this sound is 31,623 times more intense. When, in this case, because it's a 0.5, you'll notice that you may already know that this is the same thing as saying 10 to the 4 times 10 to the 0.5. Well, 10 to the 0.5 is the same thing as taking a square root. So we go 10 to the 4 times the square root of 10. The square root of 10 is 3.1623. 10 to the 4 is 10,000. So it's 3.1623 times 10,000, which is going to give you your 31,623. I don't expect you to do this, because it really only works if you're working with a nice number like a 0.5. This, plugging it into your calculator, is a much better way. That being said, you should have an idea of what range of numbers you should expect. So 4.5 means it's somewhere between 10 to the 4 and 10 to the 5. The harder one to deal with is question 4. What decibel increase represents a sound that is 5,000 times more intense? So if we look at our little formula we had, the change in sound intensity is equal to 10 to the x, where x is a change in decibel level, or in bell levels. So the change in sound intensity is 5,000. So 5,000 equals 10 to the x. How do you go about solving this? We know that we say, well, when we bring things over, we do the opposite. So when I have something like, if it was 5,000 equals 10x, that wouldn't be too difficult. We divide by 10 on each side because we were multiplying by 10, x by 10, so we're going to divide when we bring the 10 over. So what we have to ask ourselves is, it's kind of an opposite or a reciprocal. What is the opposite or reciprocal of 10 to the x? And the answer is where we get this whole idea of logarithm. What we have to do is take the logarithm of both sides. So we say log 5,000 equals log of 10 to the x. By definition, this is a mathematical definition of what a logarithm is. The logarithm means what number, so if we take the log of 5,000, we're saying what number satisfies the condition 5,000 equals 10 to the x. So in this case, if we're taking the log of 10 to the x, what number satisfies that? So 10 to the what is equal to 10 to the x. Well, that's an easy one. It's x. So by definition, this value right here is x. Because taking a log means 10 to the what equals the number that is after it. So 10 to the what equals 50. That's what log 50 means. So log 10 to the x, 10 to the what equals 10 to the x. Well, it has to be x. At the very least, even if you don't quite understand the reasoning behind this, at the very least, you should be able to plug the numbers in. You'll learn about logarithms in more detail in your math classes. So if that's x, we have to figure out what the log of 5,000 is. And I don't expect anybody to do this in their head, except for numbers that are even factors of 10, like 10, 1,000, 100, 10,000. 0.1, 0.01, and so on. So if I type in 5,000 in my calculator and I press the log button, it gives me 3.7, we'll say. 3.69897, so we'll say 3.7. And that number makes sense because 10 to the 3 is 1,000. 10 to the 4 is 10,000. So 10 to the 3.7 is going to be somewhere in that range, between 1,000 and 10,000. And so 500 hits that range. So therefore, the sound intensity went up by, I think it was up 5,000 times more intense. So sound intensity went up by 3.7 bells, or 37 decibels. Okay, and that's all there is to it. A couple of questions, because I don't find that this chapter was particularly, this section was particularly good in your textbook, so I left you a couple of mathematical type of questions to work on. So 7.4 in your textbook is literally one page front and back with a couple of very simple questions to answer. Here are some supplementary questions to do after you've done that. Number 1 and 2 are fairly straightforward. Number 3 is quite a bit more complicated, and that's something, if you get an answer for this and you want to go over it, if you get an answer for this, even if you don't want to go over it, check in with me, show me what you've got, and I'll see what your process looks like.